I'm introducing a new model other than the hybrid pi model called the T model. Why? Because it's sometimes more convenient to use this alternative model instead of the regular hybrid pi model. So how does it look like for a PNP? How does it look like for a NPN? So let's start with the NPN T model, the NPN equivalent of a T model of a transistor. So it's called the T model because the three element of or ports of the transistor are represent the form of a T letter. So as you go from the base, you've got, and this is NPN, so IB flows into the base, okay? And when you reach a common point, that's is still the base basically. And from there, you've got the current source of showing the collector current. So that's the collector then, with IC flowing that way. And on the other side, before you go to the emitter, of course, you go through a resistance, and then only you reach the emitter. But as you go from the resistance, what resistance is that? I would like you, when you get to this point, to guess. It's gonna be either R pi or RE, just as a hint. Now, will it be R pi or RE? Remember, whether it's R pi or RE depends on how much current is flowing through it. So what is the current here? It is IE, because it is the combination of IC and IB combined to form IE. So since IE is flowing through there, that means this is definitely RE. So that will mean that a voltage VBE is applied, VBE or V pi is applied from the base to the emitter. So this will be the NPN small signal analysis equivalent circuit in T model. So alternatively, we also have another mode for PNP. And when it comes to PNP, obviously we still have the base, but the current flows out of the base in PNP, as we know. We reach that common point. From the base, we go to the collector, but as you go to the collector, we've got the current source, which is pointing up because it's also flowing out of the collector. And as you go to the emitter, these two currents, IB and IC, actually come from the IE current that has split. So IE, which means as we reach the emitter, on the other hand, we've got RE, and that is due to a plus minus VEB, not BE, but VEB, which is the same as V pi, which is causing IE, okay? Forwarding biasing the emitter to base junction. That will be the equivalent for a PNP. So this is what we call a T model, and we will refer to it in some instances. Okay, so let's carry on with the AC analysis. Now that we know what the transistor can be replaced by while doing our AC analysis, we still have to look at other aspects of a circuit that need to be and how they behave as we move to AC analysis. So during AC analysis, and here we're looking at other aspects other than the transistor, because we know what we can replace the transistor with. We replace it with its small signal equivalent circuit. Sometimes hybrid pi, sometimes T model. But what about capacitors? And this is the beginning of definition of some rules that define how you start AC analysis to convert your AC, your DC, your given circuit. Sorry, your given circuit. What does it become when you're doing AC analysis? So capacitors. Now that we're in AC at a certain frequency, operating at a certain frequency, they will have a certain level of reactance, which will be 1 over 2 pi Fc. And for that matter, and for simplicity's sake, in electronics 2, we will consider them like short circuit now. Although we're going to go into more details in electronics 3 in terms of what is the impact of capacitors on the design of the amplifier. But for electronics 2, capacitors, while doing AC analysis, behave like short circuits. Very important, and very important to apply. It has got a lot of consequences because, for instance, if we had a certain circuit like that where we had an emitter resistor and it was bypassed by a capacitor, for instance. When we're doing the AC equivalent circuit, the capacitor will behave like a short circuit. Then we'll suddenly end up with 0 ohm in parallel with RE. What is 0 in parallel with RE? It's 1 over 0 plus 1 over RE to the power minus 1, which is infinite, plus anything gives infinite to the power minus 1, which is 0. So that will be equivalent, basically. Of course, the transistor will be replaced by its T model or its hybrid pi. So at the end of the day, in AC, it will be as if there's no resistor there. So these are the implications of the capacitor behaving like a short circuit. We'll see more of that. So now, what is the other rule that kicks in when we're doing AC analysis, that and how it affects the rest of the components in the circuit? All the DC voltage sources, become ground. Why is that so? If you're trying to measure how much AC signal you have in a DC voltage source, you've got your VAC value of a DC voltage source is actually 0. That's why DC voltage sources become 0. Okay, so they will behave like grounds, basically. Okay, that's very important to remember. The other thing is, although we don't in this specific case of electronics too, we don't do amplifier circuit with current sources, but normally your current sources would have behaved as open circuits. Current sources in AC, current DC sources, sorry, would have behaved like open circuits. So DC voltage sources behave like grounds. So what is the implication of this? Let's say you had a circuit, a transistor amplifier circuit like that, where you had RB1, RB2, and you had VCC there, and you had ground here, for instance. And this is just part of a circuit. Then, if for you to do DC analysis, VCC, which is a DC voltage source, will become ground. Then you suddenly are having RB1, instead of being in series with RB2, like it was in DC analysis, because now we've got ground there. Now we've got ground and ground, which means it's the same point. So you are sort of having RB2 going from that point. You can call that point A. So going from point A, you're having RB2 going to ground, and you're having RB1 going to ground. Then from the same point A, you go into the transistor, because there you are going into the base of the transistor. So that means now you suddenly are actually having in AC analysis RB1 in parallel with RB2. Okay, so that's a consequence of the fact that all the DC voltage sources will become ground. That's a second rule. Now, which other rule is used when doing AC analysis? Capacitors become short circuits. DC voltage sources become ground. Okay, that's very important. And we know that we replace the transistor by its small signal equivalent circuit, either the hybrid pi 1 or the T model 1. Okay, I think that, and current sources, if there were any, would have behaved like open circuits. Now, for us to practice this, we will now look at analysis of different configurations, because when BJTs are used as amplifiers, they can be designed as amplifiers in different configurations. But we actually have three main or core configurations. These include what we call common emitter configuration, we will have what we call common base configuration, and we're gonna have what we call common collector configuration. Each of these configurations has their own merits and demerits, as we'll notice. But what does it mean, common emitter, common base, common collector? Let's start there. So remember, a transistor is a three-terminal device or component. So component, but an amplifier is a two-terminal component. There must be an input, there must be an output. That's it. So now, when you use a three-terminal component as a amplifier, which is a two-terminal device, one of the terminals of the transistor will behave like the input, the other one will behave like the output. But there will be that one component or terminal from which you can do observation on the input and you can do observation on the output. So which is common to the input and the output. And that what defines a specific mode in which you're using the amplifier. So when the emitter terminal is the common terminal between where the input is applied and where the output is taken from, then you speak about a common emitter. So what that means is that on a transistor NPN, for instance, like this, if the input signal, meaning the signal to be amplified, the source signal to be amplified, is coming in through the base, and the output signal is taken at the collector, for instance, that way the output is taken at, so V in is coming into the base. So it's a source voltage which can be reduced by some source resistance. A typical example is a microphone. You put your voice in, it picks up your voice, but when it comes out of the microphone, it forms the input Vs, the source voltage, to be amplified. But between the microphone and the amplifier, there is a wire. So that's why it introduces a bit of resistance that we call the source resistance, for example. But eventually Vs transforms in Vi, that actually gets amplified. But the point I'm trying to make here is that the input is at the base, the output is at the collector. The emitter has got no input, no output. So input is there, output is here. So the emitter is the observation point from which you can observe what's going on the input side and on the output side. So that what forms what we call a common emitter. So in a PNP transistor, obviously, it can be drawn by like that, of course, as you know. In this case, that's the collector, the emitter, and that is the base. But sometimes it's also drawn like this, where this is the emitter, that is the collector, and that is the base. So the fact that we apply the input, it's coming in the transistor through the base. The output is taken from here. You shouldn't be confused. A lot of students tend to confuse and say this. They confuse the emitter and the collector, forgetting that in a PNP drawn like this is the emitter. So the output, if it's taken from here, this is still a common emitter amplifier. So it's not about how it looks, it's about the concept, right? When it comes to common base, NPN once more, a common base, which is a second configuration. So the base is common terminal to input and output. In a common base amplifier, the input is applied at the emitter. Input is applied there, the output is taken at the collector. And the base is common to that's the observation point from which you can look at the input, you could look at the output. So you observe from the base, which makes it a common base. In a common collector, the collector is the terminal from which you can observe what's going on at the input and what's going on at the output. So the input comes in through the base, the output is taken at the emitter. Input. There can be secondary in between, but the point is the source voltage or source input to be amplified comes in the transistor through the base, while the output is taken at the emitter. So the collector remains the observation point from which you can observe what's going on at the emitter, what's going on at the collector. So that's what we call common collector. So now you understand the concept of common. Okay, so we're gonna start with common emitter.